All right, everyone. Thanks for joining us today. This is Adam Green from ATA Engineering, welcoming you to this ATA webinar on battery design workflow. I'm joined by John Wilson from Siemens, who will give us a lot more detail as the second presenter. A few housekeeping things. Everyone's mic is muted right now. And if you need to ask questions, if you look on the Zoom interface, there is a Q&A chat window where you can type in questions. At the end of the presentation, we will open up both audio if needed, if somebody wants to talk, or we'll respond to all of those Q&A questions. And the other thing too is that this webinar is recorded, and so it'll be shared on ATA's website and our YouTube channel. And so you can share it with others in your company if you want to. That normally takes about a week from the end of the webinar before it gets posted. So welcome. So we're going to talk today about a battery design workflow, really from cell chemistry all the way to battery management systems. But before we do that, I am going to just do a few slides on who ATA are relative to Siemens and why we're here talking to you today. And so ATA Engineering, if it will update, there we go. We are basically an engineering consulting firm, and we specialize in high-value engineering services, and we work in various markets from aerospace to spacecraft and defense. And really, we do very normally hard problems that most other engineering groups, won't tackle. So we really specialize in the harder problems for the toughest product design challenges. And we do that with a team of very qualified people. Over 210 of us now around the US, over 100 masters and over 40 PhDs. So you can see that we have a lot of skilled people, including professional engineers. And we really go from design through analysis. And also one of our big groups is in testing, mostly aerospace structures. And so we really go through the whole process from design, analysis, and test at an extremely quality level. And if you've ever or never heard of ATA Engineering, really we're tied quite closely with Siemens, because ATA used to be a group within SDRC started in '67, but in 2000 ATA was formally created as a group that came out of SDRC. And if you know that the history of CAD tools, SDRC created ideas which ultimately became NX. NX is now owned by Siemens, and hence ATA have been involved with NX and the Siemens history, really for 25 years and beyond. And you can see from this time scale that over the years, we started to resell Siemens products. We became the first partner in 2018 to sell Star CCM Plus and HEEDS. And now we've just recently become the first partner to sell Siemens test and measurement hardware. So we're very close to Siemens. We're a platinum level partner, which is the best you can get. And we work very closely with them all the time. And we sell really most of their Simcenter, Teamcenter, and NX CAD/CAM products. We sell and support them. We have large teams that really deliver top-notch support to really any of our customers who buy Siemens tools through us. And we also provide full support on our website. If you really want to go there and ata-e.com/software, you can really pull down any info you want about Siemens tools. Talk to us, reach out to us if you want to. So please visit our website if you're interested. And so let's move on from ATA and kind of focus a little bit about what we're going to do today. And that is, we're going to talk about battery design workflow. And I've been around CD Adepco and Siemens for some time, and I'm familiar with the development of the tools over the years. Back in 2022, which is not that long ago, admittedly, there were this is how Siemens presented the technology for analyzing and designing batteries. And you'll see from John's presentation soon that things have come a long way since then. But back then, really, they looked at four crucial parts of battery design, from microstructure and electrochemistry, through actual individual cell design, then pack design, and then system design. And so when you look at each of those kind of columns, the they're all kind of very discrete disciplines, and really many different engineers were doing each one. And so when you look at those three, the number one, the chemistry, and the pack, number two, were both done with Star CCM Plus, a CFD tool. The second one, the cell design, was done with a tool called Battery Design Studio, and then the system design was done with a tool called AIMSIM. And basically now all of those tools are fully integrated together, and you'll see from John's presentation how that works. But if you look at the individual analysis tools, Battery Design Studio really lets you look at individual cells, the chemistry. It looks at, you know, assessing how a cell will perform, and really when you're designing a single cell, you know, Battery Design Studio really is an effective way to do it. And it also connects nicely with HEEDS, which is the Siemens optimization tool, which really lets you, you know, home in on the best design and the geometry for the internals of a battery cell. And really you can see here, you know, it really creates reliable cell design, you know, out of the gate. Now, a lot of people are not designing their own cells, so obviously this is, you know, only related to people who are actually looking at their cells. But many people are just doing pack design with the cell that they get from, say, Panasonic or somewhere else. And so Star CCM Plus is a CFD tool which really gives you the physics to model the full thermal side of a battery pack. And obviously, when you think about doing that, there's a lot of pieces that go into a model like that. There's the CAD side, there's meshing, there's the physics and the chemistry of the internals of a battery, and the heat generation and so forth. So Star CCM Plus, with its capabilities, is a really great platform to let you do all of those things. And when you look at the features in Star CCM Plus, and we'll have to load this next slide. There we go. Basically, when you look down here on the right, you can see that the multi-phase and the multi-physics capabilities of Star CCM Plus really equip it very well to do not only, you know, flow and cooling through a battery pack, but also a lot of the chemistry, electrochemistry, and, you know, really anything you might want to do on a battery, Star CCM Plus can do. And so it really lets you dive in deeply into the analysis. But sometimes it can take a long time, and so to do detailed analysis like that. So AIMSIM is a mechatronics tool that kind of brings together the previous two tools in an environment where you can build effectively a network model of a bigger system that will run faster, and really let you build a system around a battery use case to actually model the system controlling a battery and responses to it. And so AIMSIM is really the framework that lets you build a network model of a system that can run fast enough to really give you answers that make sense in a decent time. And so if we look here, you can see this is just an example of AIMSIM, and the network models at the bottom are pretty basic compared to, say, a CFD model, where each model is using simple equations, but it runs very quickly. So you can build a full network of a system and have it run in seconds instead of, you know, hours or days that sometimes CFD takes. So those are the kind of three tools that used to be the case. But now Siemens has continued to evolve and develop new things. And this is really, you know, a part of that is that Siemens now, and obviously many vendors, look at a comprehensive digital twin of really any product design and manufacturing process. And for batteries, you know, this is how it can look. And really, you know, if you look at the two streams here, one, you've got chemistry development, cell design, and cell performance and aging on one track. And then perhaps down here, and this is a little focused on EVs a little bit, but you may have pack development and battery management system development, and then an overall system and performance design of a pack and a system. So these are digital threads of a complete, you know, end-to-end story of, okay, how do I create my requirements, and how do I get to a product that actually satisfies those requirements as effectively as I can. And so moving on then to John's presentation very soon, if we look at the tools that create all of that from a vehicle development point of view, if you were creating an EV, you know, these are almost the steps that you would take. Obviously, you know, define the vehicle performance, define the battery pack requirements, and then you would assess the cell development that you wanted to do, and that, if you might be buying that off the shelf, or you might be creating your own, but either way you would make decisions here. Then you would design the pack based on the things that the pieces you wanted to use, and really look at the full CAD geometry of the pack to be able to do thermal analysis. Now, if you've got the full CAD, you can not only do thermal analysis, but you can also use that CAD to actually manufacture, and that's really part of the goal of Siemens, to create a full digital thread of CAD and data and really the model geometry that lets you use it in both development and analysis and ultimately in manufacturing down the road. So if you look at this slide and you think, well, okay, that looks great, but what tools should I use? Here's a list of the tools that kind of is created for each of those areas. And so obviously at the beginning, you're probably going to use Teamcenter as a PLM tool to really bring everything together. Then you might use Siemens Sim, the simple system modeler, to create a network of the battery pack requirements. And then down in here, Star CCM Plus and BDS to actually do the chemistry. Siemens recently bought a new code called Colgi, which is more advanced chemistry than Star can do. So that's coming into play as well. AimSim and then NX also are useful. So when you look at analysis, AimSim helps you do the simple 1D analysis, but Star CCM Plus really lets you look at the thermal analysis and the safety. And then really, as you get down to making something and manufacturing, Simcenter 3D and Nash transfer analysis, and then ultimately test lab if you physically want to test something. So that's the list of tools that Siemens has nowadays to really do battery analysis, and it's very complete in terms of the digital twin and the digital thread that lets you do full battery design, assessment, and manufacturing. And then this is really just another way of looking at that. Let's see if these animations will play happily. Yes, they will. Good. So really, if you want to look at material design and analysis, Colgi and Star CCM Plus will let you dive into the chemistry and the microstructure of the battery. If you want to look at basically more electrothermal, so you want to see how hot a pack is going to get, Star CCM Plus will let you do that. If you want to look at thermal runaway, then again, Star will let you do that too. So you can see here that a big part of the battery story from Siemens is Star CCM Plus, supported by the other tools. And the other thing to note is that all of these are supported by heat for optimization. So can really help dial in the best designs, the lightest, the most powerful, with matching all the other criteria that you need. So that's kind of summed up my introduction to all of this. I'm going to pass the ball to John now. John, welcome today, and if you can take the share, and over to you.
All right, thank you, Adam. Can you all see my screen properly, and can you hear me well?
Yes, we can, both.
All right, great. All right, so good afternoon, everyone. Good morning, depending on what time zone you're in. I'm a technical solutions consultant within the 3D Fluids Center of Excellence team at Siemens Digital Industry Software. And over the past couple of years, I've had the privilege, honor, challenge sometimes, working with customers in the battery cell development space, and those customers who want to integrate battery cells into packs and understand how they operate both under nominal and safety conditions using simulation approaches. The battery industry is set for an extremely high potential of growth over the next few years, and the work to develop battery production facilities or gigafactories can be high, both in time and cost, and it's predicted there will be about 15 global suppliers that'll lead the industry, according to this McKinsey report from 2022. And with such rapid growth, there are some urgent challenges that need to be addressed, such as sustainability, meeting energy density requirements, scaling up, fast charge requirements, and more. This is the map that Adam showed just a moment ago. And if we take the application of battery pack development for a vehicle, this is our overall workflow, which ranges from across scales, from performance and range requirements and sizing at the systems level within SimCenter AMSIM, all the way through to battery management system development and controls development. Each of these pieces of the workflow is mapped to a solution, which is easily linked and integrated to neighboring pieces of the workflow. I can take that overall map and essentially flatten much of it out into 6 steps, starting with material trade-off and cell design through to system and requirements validation. The battery engineering workflow also involves collaborations with other digital threads that are enabled by a PLM backbone. And I'd like to also note, while I do use a lot of automotive references during this talk, the workflow could be applied to any system, computers, battery-powered aircraft, power tools, lawnmower, many other applications. So let's start with the first step, which is material trade-off and cell design validation. This is where you may have a certain capacity requirement, weight, or material requirement, and we need to make sure our cell design meets these or at least gets close to them. You can explore the impact of materials and physical descriptions on your cell design. And for example, you might be working with a lower energy density, but safer material for the anode. So you'd need to make the size of the cell relatively large to meet the capacity requirements. This material trade-off investigation is primarily done through 0D, 1D models, so it's particularly fast. However, once you've settled on a particular design or two, you can then take that 1D data, that 3D that physics-based model that you built at the 1D level, and you can plug that in to our 3D physics-based model, which is now available through a template within SimCenter Star CCM Plus, right here. Overall, through material trade-off and cell design validation, we've calculated cell designers can reduce testing by about 30% using our physics-based model of the battery cell. You can also reduce the likelihood of prototype failure during manufacturing. This is SimCenter Battery Design Studio. It's our 1D simulation tool for cell design. Essentially, you start with a template. You can prescribe the electrode dimensions, tab information, coating height, etc. You then define the material, the formulation for the active material, the binder, the conductivity aid. You can use our database of materials, or you can add your own materials to the database. You plug in the voltage equilibrium curve, and then you can tweak the modeling parameters to suit your needs. The code can run in parallel. Here we've specified 8 threads. And then once you've defined your cell and you make sure the cell, has the right capacity and everything, you can then start defining procedures to run. So in this case, we're discharging the battery cell at different currents until the voltage reaches 2.8 volts. You can then plug each of those procedures at the various currents into a test and run the simulation. The output displays live, as you can see here. You get access to the results through our different post-processing tools within Battery Design Studio, BDS. And then once you've refined your design using that kind of fast cell design capability in BDS, after running through many different iterations, you can then plug the best ones into our 3D cell design tool, which is available through a template downloadable with SimCenter Star CCM Plus. So this is our multi-physics CFD software, essentially. all of the parameters, in fact, that you see in Battery Design Studio are essentially available here. You're able to get data across the surface of the cell. So lithium ion concentrations, electrical quantities, and you can also get them throughout the cell, so layer by layer variation. I've just shown you a demonstration of the 1D modeling tool, and which is Battery Design Studio, and how we can take that design and put it into our higher fidelity tool to build a 3D physics-based model to understand layer by layer variation in cell surface cell performance rather, and even across the surface of the electrodes. You can look at things like phenomena like localized lithium plating, for example, which could be detrimental which is detrimental to cell performance. Now, while you're still in the early stages of the design phase, there may be properties of materials you're not quite sure about or can't find in the literature. For example, lithium diffusivity within the active material or exchange current density at the interface of the active material and the electrolyte, these kinetic type of parameters. You can then segue into our computational chemistry simulation tool, recently acquired by Siemens, which is SimCenter Colgi, to back out those values or even explore new materials based on a given molecular makeup. With this part of the workflow, you can reduce the time in the chemistry lab by virtually screening molecules and formulations to determine parameters. Processes such as intercalation of lithium, lithium ion transport in the electrolyte, and diffusivity in the active material can be simulated and determined. These molecular outputs can then inform the material properties at the continuum level or at that 1D level within Battery Design Studio. There are many benefits to this type of molecular level modeling, including expanding the design space and reducing testing costs. Ultimately, you're optimizing battery performance and making the design process more cost-effective and easier. This is the interface for SimCenter Colgi. It's user-friendly, graphical, so you don't have to be a coding expert to use it. The user can define locations and connections of atoms and molecules, including the types of bonds, and you can draw from the ingredients in our database. Ultimately, you'll set up your reactions and scripts to simulate molecular activity, for example, diffusion of lithium ions within a newly formulated electrolyte. Now, once you've designed your cell, set the materials and physical properties, and studied the molecular formulation of the battery cell, you can then characterize the cell's performance and prepare for cell integration into the pack model. Now, in this step, cell performance characterization, you're able to take a single cell and predict the electrothermal response under real operating conditions. So the engineer or scientist can automatically generate test protocols and identify the cell model parameters for RCR, equivalent circuit, and aging applications. You can also identify thermal runaway physics-based parameters like trigger temperature and the energy released from battery cells. So this would be within SimCenter AIM-Sim. Basically, with this virtual performance testing, you can go 10 times faster, reducing experimental time and breaking barriers between test and simulation. You can virtually determine parameters for both equivalent circuit models, RCR, and thermal runaway models. And while ARC testing, accelerated rate calorimetry testing, will ultimately still be required to verify and calibrate thermal runaway models, you can make the investment in that expensive test easier by creating a physics-based thermal runaway model to predict that's capable of predicting different scenarios. So let's go into the tool right here. You set the battery definition that we determined from the requirements stage earlier. And then you can set the constant discharge parameters. This will allow you to identify the battery capacity and thermal parameters. You can define different hybrid pulse tests at different temperatures. And then these data allow you to identify ultimately when you simulate them, you can get the equivalent circuit parameters that are required to run these electrical type of empirical models. So to summarize what we've done so far, we've developed a cell, including number of layers, size, thickness, and material composition. We've also computed the equivalent circuit parameters during the cell performance characterization stage. And we've even used computational chemistry using Simcenter Simcenter to help determine material properties um, and even develop new materials. Now we're going to be circling back to the systems level model that was used to build the cell requirements, and I want to refine it with the cell definitions that we generate during the first two steps of this workflow. Now this is a more systems level study where we can input vehicle requirements like range, acceleration, or top speed, fast charge time requirements. We can then get an output of pack requirements, including energy, voltage, maximum power. And you can then estimate the number of cells required and make sure your earlier design, cell design that we just developed, meets these requirements. At this stage, you're really able to make sure the cell you design meets all of the pack requirements and connect your battery cell definition back to the larger integrated system. So let's take a look at how this pack architecture tool looks in action. So in this case, you'll start with high-level vehicle parameters like weight or mass, tire torque, other data. Once that data is input, you can simulate a drive cycle, could be a standard WLTC cycle like this one. And once you simulate this, you can make sure the cell you define satisfies requirements like power and voltage. And you'll also make sure the cell is sized accordingly and doesn't take up too much volume in the vehicle. Now at this point, we might need to request further testing based on our simulation results or go back to the material trade-off step. So how do we manage these requests easily and connect data through these various simulation tools? How can we keep everything organized? Well, we can do this through what we call here a battery collaborative platform. The battery collaborative platform is created through Teamcenter Simulation, which enables the user to manipulate objects from various simulation tools, and it's based on the Teamcenter Foundation. You can really speed up simulations and deliver results faster by creating a complete digital thread path from the early stages of requirements through the analysis stages. Now you can imagine how much time in a traditional and non-connected setting an analyst may spend gathering information about an input file or even providing feedback once an analysis is complete. However, with this workflow right here, using Teamcenter for Simulation, you can easily save a ton of time by including all of the data in a single platform. So here, the analyst, or the user rather, creates a verification request, types in a name here, so verification of the battery pre-sizing characteristics. That's then sent back, and so someone receives it, checks the requirements and the parameter verification requests. All the data previously related to this type of a study, this work, is reported here, and then a method to perform the verification can be input, and simulation modeled and connected all in this streamlined way. Now, once you've confirmed the cell meets the requirements and defined how many battery cells are needed in the pack, you can then move on to understanding whether your battery pack satisfies thermal requirements and is safe to implement. One of the main safety concerns is battery thermal runaway. Thermal runaway is the phenomenon of exothermic chain reactions within the battery cell. These reactions usually cause a sharp increase in the internal battery temperature, causing the inner structures of the battery to destabilize and degrade, which can lead to total failure of the battery itself. And you want to really avoid thermal runaway at all costs. However, if it does start to occur, we want to slow the propagation within the pack as much as possible. There are a few ways to tackle this, and the first is in which we'll try to do that is through modeling thermal runaway using a physics-based model in SimCenter AIMSIM, and the second is using a high-fidelity 3D approach. One of the main benefits of these thermal runaway models is, again, you can reduce testing costs by identifying a physics-based thermal runaway model capable of predicting heat release and gas venting under different scenarios. You can really just ensure more confidence in the safety of your vehicle or whatever application you're working in. And with the 3D model that I'll show in just a little bit, we have a dedicated thermal runaway configurator that makes setup relatively seamless. This is within SimCenter AIMSIM, we have an Arrhenius-based thermal runaway model. You can generate different scenarios, different levels of heat source, different states of charge, different states of health for the battery, and we can see how these affect the temperature of the battery during thermal runaway. So we can run these simulations quickly. This is a 1D type of a tool. And so we can look at how does that state of charge affect the temperature at this particular port. We can then also plot the impact of aging here. So different states of health, how does that impact that temperature as well? We can also get data, for example, like the venting mass flow rate from the cells that we can directly save as an external file and then use as an input for the 3D thermal simulation. And here you just see a representative video of the file being saved. And then we can move on to the next step, which is the 3D thermal modeling. So in Star CCM Plus, we have a really robust and streamlined workflow capable of handling thousands of parts, which you might have in such a battery pack as the one shown here. We also have ways of handling those very thin parts in the battery pack structure. We're zooming in here to the battery cell casing, which was meshed using our thin mesher. So taking advantage of that high aspect ratio of those thin coverings. And then here's the data that we would have input from SimCenter AIMSIM. So the heat rate for the solid part of the battery and then the venting. So when the battery starts to vent, we need to prescribe these data either through like simulation results from AIMSIM, like I just showed, or from experiments. So in this case, we have our battery thermal configurator, thermal runaway configurator rather, where we can specify the venting. So we put in the data for that vent table, the mass flow rate, temperature, and then we can also set an initial core part density. So this is the initial density of the cell. As the cell vents, there's obviously mass loss, and that's handled automatically within this thermal runaway configurator. We can set activation constraints. So, typically we use a trigger temperature. So at what temperature does that battery cell have to reach in order for the thermal runaway model to take over? Here it's 408.15 K. And we do a similar setup for the solid heat release. So two mechanisms of heat release, the venting and then the heat release of the solid. So the 3D CFD simulations we can perform for thermal runaway, like I just showed, are easily set up using the thermal runaway configurator. You import the solid heat release and venting data into the battery module, and you set any model activation constraints such as thermal runaway, trigger temperature, and maximum energy release. We can set that maximum energy released to make sure that we don't get any unrealistic, unphysical type of results, just to constrain the problem. And we also have a dedicated post-processing objects for gas venting and heat release. And I put together a POC not too long ago for an EV manufacturer. And really within just a few clicks, I was able to set up post-processing for a 184 cell battery pack. In summary, for the safety component of our workflow, I just showed how we can use a physics-based model within SimCenter AIMSIM to determine the effect of different on thermal runaway temperature distribution, temperature values across different states of health, state of charge, and heating profiles. And that model can inform the 3D model in terms of venting flow rates and heat release values. And you can then get a high fidelity understanding using star CCM Plus of the thermal runaway propagation through the pack in 3 dimensions. Now I'd like to now move on to the consideration of the pack under nominal or normal operating conditions and thermal management considerations during that time. This step really involves understanding how well you're cooling the battery pack, which is typically done through a liquid-cooled channel. One can easily make design changes at the 3D level to the cooling loop, like adding bins or bypasses, and these can be incorporated into the CFD model. You'll get an understanding of how much heat is transferred from the pack to the coolant, and if there are any hot spots that need to be examined. So with this 3D pack level analysis, you can really reduce prototype and testing needs while exploring even more concepts. And our established workflow for electrothermal coupling allows you to have a relatively short time for setup. You're ultimately able to ensure decision confidence by doing even more tests under real operating conditions. And basically with this thermal coupling, what we do is we have the equivalent circuit model running alongside the thermal CFD conjugate heat transfer model. What happens is that the equivalent circuit model, based on the electrical activity, the battery discharging, for example, we produce a heat, a Q value. That Q value is then at each time step transferred to the conjugate heat transfer CFD side of the model, and that's used as an input to the governing equation for energy so that we can account for the heating in the CFD side that's attributed to the electrical activity. What happens on the CFD side is that you have a volume average temperature that's computed for each cell, so one T value, and that's passed back to the lumped equivalent circuit model at each time step as well. And so this is how they're connected, okay? This is the interface to SimCenter Star CCM Plus. Here I'm showing a view within our 3D CAD tool. It's a really great tool for manipulating CAD. We exported this CAD in from an external package. We did a lot of cleanup. We can easily, add these operations, delete features, move surfaces. We just executed those. In this case, we're directly linking using Star CCM Plus client for NX to the NX file. So this CFD model right here, we can make a design change within the interface of Star CCM Plus that'll update within NX and propagate through so that we can have a streamlined workflow, and just within a matter of clicks, we can update the entire model all the way from geometry, obviously, through to the patterning of the cells, the battery cells rather, and through all to the volume mesh, which you can see here. If you zoom in, you can see the polyhedral mesh with prism layers used to define the coolant. The parameters for the equivalent circuit model, like I showed earlier, were during the cell performance testing, were determined within SimCenter AIMSIM. You can directly link those here into the electrothermal configurator. For the battery model, we have different values for the parameters across different temperatures, and there's easy post-processing for the results within Star CCM Plus here. You can also set up an optimization study in just a few clicks. So here we're running an optimization case. You specify the number of designs to run. This is through our Star CCM Plus Intelligent Design Exploration tool. And then we can get things like this parallel plot to understand, how much of an effect um, do these different design changes make on our model, and the results of our model. And so with the 3D pack level analysis, again, you can reduce prototype and testing needs while exploring new concepts, and use this design optimization to really hone in on the best design for your battery pack. In this case, we were kind of looking at like that coolant channel design. Obviously, the 3D type of models can take a lot of time to run. We developed a detailed 3D model to understand the cooling and venting of the cells, the thermal and electrical behavior. However, this comes at quite a computational cost. And this is where we can use our reduced order modeling capabilities to significantly reduce runtime. So let's go into that. This is our Simcenter reduced order modeling tool. You can create a new file and then import the data from those CFD simulation results that we got within Simcenter Star CCM Plus. Just spot check and make sure that the data is read in properly. The columns are as needed. And then you can specify what data sets are used for training and what sets are used for validation for the reduced order model. You can also set which parameters are going to be which values are going to be inputs and which are going to be outputs. You might want to test a variety of models to see which one works best with your data. So response surface model, Gaussian process, neural network. Each of these, may have a different, you may have a different level of confidence in based on the training and validation percentage results. And then after this is completed, you could essentially take this ROM and plug it into a network model where you'd be able to simulate rather and couple easily those high fidelity 3D CFD results, kind of condense them down into a reduced order model and plug that in as a component into your network model in AIMSIM. We're just showing right here that, we were able to take a simulation of 2200 seconds of physical time, and we were able to run that case in 40 milliseconds. So needless to say, you'll have a significant reduction in runtime. However, you can still preserve the fidelity of the 3D model. I'd like to also just touch on the fact that it's important to include pack structural testing simulation to ensure integrity of the solid parts of the battery under both nominal and safety compromising positions. And finally, we're at the stage of integrating what we've learned back into the entire system model. So we'll plug everything back into a wider systems level model within SimCenter AIMSIM to make sure the design meets all of the requirements such as range and thermal comfort of the vehicle. And in this systems level model, like I just mentioned, we can include an embedded ROM, an embedded reduced order model type component, so that we developed using SimCenter reduced order modeling to get the 3D fidelity in a much faster time. And this represents the full model for simulating the battery inside a vehicle along with the thermal management systems. We can then segue into a separate digital thread, which is BMS development and integration. And you can use the data from the accelerated battery cell development workflow I just presented to validate the battery management system ability to manage an efficient utilization of the battery energy while ensuring safe operation. These are our four SimCenter pillars: go faster, model the complexity, explore the possibilities, and stay integrated. In the context of our accelerated battery workflow, um, how we can efficiently simulate multiple scales of the battery development process, all the way from molecular to single cell and pack. Our integrated and streamlined workflows allow you to seamlessly make changes to parameters for both the geometric and boundary condition types. And all of this can be supported with a Teamcenter for Simulation backbone, allowing everything to be integrated and organized. And with that, I'd like to thank you for your time and happy to answer any questions you might have either through the chat or if you unmute your microphone. Thank you.
Thank you, John. That was great. We appreciate it. If anyone has any questions, please put them in the Q&A chat right now. John, I had one question, and that was basically when you look at all of these tools integrating together, let's say you want to make AimSim and Star talk to each other very easily. Are all of those connections embedded in each of the tools, or are there additional kind of licensing things you need to think about, or are the interconnects already in place?
Essentially, the interconnects are all in place, Adam, in the context of connecting SimCenter Star CCM Plus and SimCenter AimSim.
Yeah.
We saw, there were a lot of demos in that presentation, but we saw that, for example, you can build the equivalent circuit parameters within SimCenter AimSim, and there's a direct node within Star CCM Plus to bring those in, dedicated to SimCenter AimSim. And those are the equivalent circuit model parameters for that electrothermal coupling.
Okay.
Also, with SimCenter Star and AimSim, we support functional mockup interface, which is an open source format for kind of doing co-sim essentially between these two codes. Yeah.
Excellent. All right. And so one other question: when you take Star CCM Plus as a whole, I think you need to add Star CCM Plus batteries to the model, right? You need both of those to make this work.
Yes, yeah, to do the thermal runaway modeling with the venting heat release, or even the electrothermal modeling using the equivalent circuit approach, you do need the batteries add-on, along with, a Star CCM Plus license.
All right. And so, what does that add-on give you? It basically gives you the chemistry of the batteries.
Yeah, it basically gives you the capability of using that thermal runaway configurator tool that streamlines the process of the thermal runaway setup. You also get the ability to model the electrothermal coupling aspect. So that RCR equivalent circuit model produces the heat. The CFD side produces the temperature, and they couple to one another. You also get access to the 3D cell design template that I showed. So that's essentially where you can look at variations and explore the cell kind of electrochemistry side of things, look at lithium ion concentrations across the surface of the cell, or through the cell layers in detailed 3D. Yeah, the physics-based model.
All right. Excellent. Thank you for that info. That's very useful.
Yeah.
So I think there aren't any other questions on the chat right now. So I think we'll wrap up this presentation. Thank you everyone for joining us. It's been a pleasure. Thank you, John, for your presentation. That was great. And this overall webinar will be on ATA's website and our YouTube page. We will send out locations for that to everybody who attended. So please feel free to share that so that other people can look at the material. So with that, thank you, John, and thank you everyone for attending, and we will close the webinar.
All right, thank you.
Thanks. Bye-bye.